Hey, welcome back. Let's do another example that as you look at it, as you approach it, you start to realize it's best to approach it in a polar way instead of a Cartesian way. And again, now this is going to be an application. Just like we approached all of these questions from for double integration, and we had a number of different applications: mass, center of mass, charge, um, density, mass density. You put all of those things, we can now apply them with our new technique in terms of polar integration. So here's what we're going to set up. We're going to say we have a point on a semicircular lamina of radius a, where the density is proportional to the distance from the center of the circle. Find the mass of the lamina. Wow. All right. So let's draw a picture. You always want to draw a picture. All right. So what we're saying is we have this semicircle, and the radius of the semicircle is a. And what we're saying is that the density is proportional to the distance from the center. So if you're at a distance 0 from the center, then it's basically not dense at all. But as you get further and further from the center, the density gets denser and denser. It gets heavier and heavier as you move out. You can think it's really, really thin in the middle, and it's getting thicker and thicker as you go out. So if we were going to set this up in terms of a Cartesian setup, what we'd probably do is we'd say, okay, so this is a circle. We have x squared plus y squared is equal to a squared, and we have the top half. So this is the function y is equal to square root of a squared minus x squared. We need an equation for the mass of the lamina. Well, it has to do with the distance from the center. So the mass density is going to be what we normally write rho of x and y for that. And so the mass density is going to be some constant times the distance, square root of x squared plus y squared. And so you'd set up an integral that looked like this, an integral from negative a to a, of the integral from 0 to the square root of a squared minus x squared, of the density, k square root of x squared plus y squared, dy dx. And you wouldn't want to do that integral, but you could set that up. So we're noticing something. We're noticing some circles centered at the origin. Great. We're noticing that our function has x squareds plus y squareds in it. These are all bright lights telling us that we should be using polar coordinates instead. So instead, if we were in polar land, our region is now the top half of the circle, where we have radius goes between 0 and a. Theta goes between 0 and pi. Yay, it's a polar rectangle. All right, so that's our domain. And then what about our function? Our function rho of xy, oops, sorry, not rho of xy, because we're not dealing with x and y. Instead, what about rho of some coordinates r and theta? It's going to be some constant times the distance you are from the origin. So k times r. And so no matter what point you are, k times r is going to be, so when r is 0, no mass density. When you're out at the origin, it's k times a. And so this is a much nicer equation. Nice equation for density. And so then we set up our integral. Integral from r is equal to 0 to r is equal to a, theta equals 0 to pi of our mass density, which is kr. And then don't forget your r dr d theta. And that gives us our much nicer integral to integrate. Just like before, we really do have a function of r times a function of theta. So we can write this as an integral from r equals 0 to a of r squared dr. I'm going to even bring the k out. And then I have an integral for theta equals 0 to pi of 1 d theta. And I can then just multiply these two integrals together. What do I get? K times r cubed over 3 evaluated from 0 to a, theta evaluated from 0 to pi, which is pi. So the final answer would be k pi r a cubed over 3. That would be the total mass of the lamina. And I guess that would be in kilograms, if it's in kilograms to start with. All right, so there's another example of using polar coordinates to do a polar double integral. All right, see you next time.